Today we're going to derive the governing differential equations for the liquid heights in two different tanks. So first, always let's start by drawing a picture. So we have two tanks filled to a certain height with liquid. So we'll name this tank 1, and tank 1 has a height of fluid H1 and a cross-sectional area of A1. And then we also have tank 2. So tank 2 also has a height of fluid H2 and a certain cross-sectional area A2. And so writing it in area and height, because we're gonna look at the volumes, but we wanna know how the volume changes depending on the height of the fluid. And so coming into our tank is a certain flow rate Q1, and then tank 1 and tank 2 are connected through flow rate from tank Q1 to Q2, so that's just flow rate from tank 1 to tank 2. And then tank 2 empties out at a flow rate of Q2. And so in the problem, so we don't know what Q1 is, it's whatever value, but we are given the flow rate from Q1 to Q2 is equal to 1/2 height of our fluid of tank 1 minus the height of our fluid of tank 2. Our flow rate that exits tank 2 is given as 1/4 of height 2. So this is going to be important once we try to actually solve the initial value problem in Python. So I'll just let you keep that in your brain bank. Okay, so one thing we do know, where we can assume, is that this is a steady state problem. And so this means that our flow rate going in is going to equal our flow rate going out. And so we want to look at a change in volume. We do know that, so we want to look at our change in volume over our change in time, because we are working with flow rates. Well, side note, volume equals area times height. And so for tank 1, we'll focus on tank 1 first. We can say that our change in our area of tank 1 and the height of our fluid of tank 1 over time equals our flow in minus our flow out, because we can write this as Q in minus Q out equals 0, or whatever value we want to set it to. And so Q in is just Q1 minus Q1, tank 1 to tank 2. And so when we're looking at this equation, we can sort of simplify it. The only thing that's changing right now is our fluid height. The area of our tank is always going to be constant. We can't shrink our tank and we can't enlarge our tank. So we can move it over to this side because it's constant. And so we have the change of our fluid height of tank 1 over time, equals our flow rate in minus our flow rate out over our area of tank 1. And so now we just have to do the same thing for our tank 2. So our change in volume of tank 2 over time, as our fluid flows in and out, equals the change in area of tank 2 times the fluid height of tank 2 over time. And so the fluid coming in is from tank 1 minus the fluid coming out is whatever is exiting at the flow rate of Q2. And again, the area of our second tank is constant, so it's not going to change. So we can bring it on the other side to simplify. So the change in fluid height of tank 2 over time is equal to the flow rate from tank 1 minus the flow rate out of tank 2 over area 2. And so these equations right here are what we are going to use in Python to solve the initial value problem. Okay, so now that we just found our two equations, we are going to use Python to solve it for us for the initial value problem. So I first put in all of this top stuff, and that is what allows us to use things like square root, create our plots, and all that good stuff. So kind of like behind the scenes. So we're going to start by defining our function, which is our change in height, our change in time, and we're going to use the variables t and y. So our first height is going to equal an array, and so we'll do this will be important for later. So our first array, and then same thing for height 2, second array. I'm using an iPad, so it's a little bit different. Next, we are going to type in the flow rates that was given to us in the problem. So the flow rate from tank 1 to tank 2 is equal to alpha 1 times NP dot square root of our height 1 minus our height 2. And then also we know our flow rate out of tank 2, which equals alpha 2, and we will define those later, times NP dot square root of height 2. Okay, so now we're also going to define the equations that we found. So our change in height over change in time from tank 1 equals n of t, and qn of t is just what is coming in. It's q1, and that's going to be a function times q from tank 1 to tank 2 divided by our area of tank 1, and then our change in liquid height of tank 2 equals our flow from tank 1 to tank 2 minus, obviously, our flow out of tank 2, and divided by area 2, which is just the area of our tank 2. And then turn, and then we want these values. Okay. So next we are going to define alpha 1 equals 0.5, which we know because it's given, and alpha 2 is going to equal 0.25. The area, cross-sectional area of our first tank is going to be 1 meter squared. Our second tank is going to be 1.5 meters squared. And so the reason that we sort of use a lot of variables within our equations is we don't really want to create a single number, because what if we are trying to implement a new piping system with different tanks, and we are deciding between tanks of different materials, and those tanks of different materials come in different sizes. So we need to be able to change those sizes to understand how the flow rate changes and how our piping system would need to look, theoretically. And so what we're going to look at are two different heights. So we'll set the array as 2 meters and 1.5. And so then we're looking at this over time. And so we're going to look at this over 100 seconds. So our end time is 100. And then we want to look at our Q1 values, or our Qin. And so Qin V equals, so we're gonna look at, and so this is going to be what is entering tank 1. So we wanna look at 1, 1.5, and 1.5. And so at these 3 points, we wanna look at the times. So our times in that we're like looking at, that we wanna change, is gonna be at 0 seconds, at 50 seconds, and then also at whatever we want our end time to be, which we had said about earlier was 100 seconds. Okie dokie. And so then Qn equals, we're gonna interpolate Q underscore, pardon me, Qn underscore T, Qn underscore V, and then kind equals. So we're looking at the previous, so above, perfectamente. Okay, and so now what we're going to want to do is we're going to work on solving the initial value problem. So looking at our change in height over the time interval that we had specified. And we want to be able to see what that height is. We want to be able to see what height value you get, which is h by I. And then the method we're going to use is Rado, which is gives us something precise. And then our dense output is going to equal true. Nice. So T, which is our time, equals, oopsies, in space from 0 to whatever end time is, 100. And so this sort of array that I just created is our starting point time is 0, our ending point is whatever we set our end time to be, and then 100 splits it into 100 intervals, which gives us 1 second intervals. So we can look at how it changes every second and then solve for our answer. And so this will give us our output. Oopsies, perdona. So, as we are a function of time, so let's verify this works before we graph. Spaghettios. So at line 3, import, up top, import, this should be goofy me. This should be from, because import's the second word. That's just me being a goofy little goober. All right, let's try running that again. Make sure there's no errors. Ooh, line 30. Qn equals interpolate. Oh, it looks like I used a period and not a comma to separate. Let's try that again. Oh, cute. Qn equals, it looks like I used an L and not a 1. Let me verify. Qn equals V, kind equals, okay. 32. Let's see. Res equals solve underscore IBPDHDT. Let's see what it says. The following arguments dense output equals true. Okay, looks like we have 2. Why did it say alpha 28? Oh, that's because I was typing on an iPad and I have to use shift. So that'll solve that problem, but let's look at line 32. Not sure. what's going on here. Trace back most recent call in module. Okay, so I just retyped that line because obviously I made some sort of syntax error, but my mind couldn't figure out where it was, so I was like, screw it, I'll just retype it, which I did off camera, but we're back and we're better than ever. So now we're going to plot our little graphy graph. So let's use gonna make our figure. So let's make this graph. Oopsies. So we're gonna set our columns and our columns and our rows. And then now let's define, so we're gonna have 2 lines, but we need to define what their X and their Y values are going to be. So let's do our first tank 1. So we know that X is going to be our time because time is our independent variable and our height depends on it. Our Y equals what we got above. So this is the solution from using our array that we originally created earlier. And then we're gonna name this baddie 1 for the height in tank 1. And then we're going to do the same thing to tank 2. Obviously, we know our X is our time, our Y is our solution using creating an array, and we're gonna name this baddie H2. And then next we're just going to do like the beauty part of it. So figure update. So the layout. That's the word I was looking for. So we're gonna set our width equal to 500 and our height to 400. And then we're gonna create our legend. So obviously we need to label everything. And this is just putting this in the center. When you do legend underscore X anchor equals center. So this centers our legend on our graph. And this places our legend below our graph. So like under everything, we say, oops, better than that, underscore Y equals negative 0.2. And then we're gonna name our x-axis. Wait, let me just put that under here so we're not going crazy. We are going to name our x-axis time with the unit of seconds. And then we're gonna name our y-axis, oopsies, H1 and H2. Because we're looking at the heights of our fluids, height 1 and height 2. And then, oopsies. We are gonna show our grid just for some aesthetics. If we're vibing it. And then our counter for our x-axis is by tens. 10 to 100, obviously. And then let's title our graph. 2 tanks vibing in series. Obviously, if you're giving this to your boss, don't write vibing, but I'm not gonna give this to work. And then the title, we're gonna set the center, x equals our size, 0.5. Oh shit. Oh, pardon, I did not mean to curse. Oh yikes, that's on me. Let me delete this. And then that should be good. We don't need anything else. And let's show this baby. Print her out, let us view it. Oopsies, I don't know. Hopefully, oh my gosh. Invalid syntax. What? I'm sorry. Hello? Oh, you know what? You know what? I think I'm missing a parentheses. Okay, run this. Oh, this is, I love this. Let's see where we missed. Figure, line 36. Figure equals make underscore subplot. Rows. Oh, it's rows. Forgotten S. That'll do you, boys. Oh, perfect. Oh, wow. That's pretty neat. So now we can look to see, wait a second. No, wait, yeah, that's right. Now we can see how the liquid heights, fluid heights of our tanks change over times as our entering flow rate changes. Neat.